So this is the video that we'll watch before worksheet number 6. It covers chapter 6 of the textbook, and the file name in the web page files area is phys8slides06.pdf. There are very few results from chapter 6 that you need to remember. As a matter of fact, the only 2 results that you actually need to remember from this chapter are the definition of the center of mass, which is basically a mass-weighted average of position. It's like a weighted average of position weighted by mass. So mass 1 times x1 plus mass 2 times x2, and so on, up to mass of the nth particle times the x position of the nth object. And then in the denominator, the sum of the masses of all the objects. And then there is the derivative of this same quantity with respect to time. And the masses don't vary with time, but the positions do. So you get mass 1 times the x component of velocity 1, plus mass 2 times the x component of velocity 2, and so on upstairs, and then downstairs you get the sum of the masses. So this is just a mass-weighted average of the x components of the velocities of all the objects in a system. So this is the center of mass position along the x-axis. This is the position along the x-axis of the center of mass of the system. This is the velocity in the x direction of the center of mass of the system. And if you look at the textbook instead of saying cm, it will say zm. But the textbook will call this same thing the zero momentum velocity, because it's the velocity of the frame in which the system itself, or the system's center of mass, has zero velocity. So there are almost no results you need to remember from this chapter. So if you do skim through, it'll basically just be ideas and not math results. Anyway, so I think you should first watch my video, which should cover the key points. And you could stop there if you want to, or if you want to, you can skim through and kind of look at the checkpoints, especially the checkpoints for the concepts half of the chapter. Okay, so why is chapter 6 there if there are so few results in it? Well, the purpose of chapter 6 is to build up some intuition that is going to help us, once we reach chapter 8, to better understand forces. If you took physics before, you probably introduced forces in the second chapter of the book. So forces are introduced much later in this book, because forces are an extremely counterintuitive topic, and it really helps to prepare your mind for forces before studying them. So chapter 6 is again part of building up some intuition to prepare your mind for this extremely counterintuitive concept of force. I think your patience with this approach will soon be rewarded. Once we reach chapter 8, we'll be using Newton's 3 laws, and we will then continue to use Newton's 3 laws throughout the rest of the course. So chapter 6 and chapter 7, if you go through the textbook, or maybe just skim through, especially the concepts part, they will take some time to read if you read them, but they actually add almost no new equations, so-called quantitative results. Chapter 5, energy, and chapter 8, force, will get a lot more lecture time and a lot more worksheet time than chapter 6 and chapter 7. If you're a little bit tired of the pace of going through 2 chapters a week, there's really only one substantive chapter this week, which is the energy chapter, chapter 5, that you did in the previous lecture. And there's really only one substantive chapter next week, which will be force, which will be the second chapter we'll cover next week. By the way, we're going very quickly through the early chapters of the textbook, and we're going to slow down for the more difficult topics. So chapters 10, 11, and 12 are the most difficult topics in the whole course. So the course will be, conceptually challenging at that point. And then after we get through chapter 12, then it'll be kind of another downhill where you get to apply all the knowledge that we've gained in a way that I think will be fun for you. But the conceptually hardest part of the material in the course is 10, 11, 12. Okay, so anyway, this faster pace now, I think it lets us make more time for the kind of structures applications that will come in November. By the way, where are we going? So, by the way, so about half of you, maybe a little more than half, two-thirds of you have Professor Wesley as your academic advisor, and Professor Wesley has been telling me for about 10 or 11 years now that a piece of advice he got when he started out in teaching from one of his mentors is that a course should tell a story, and every lecture, or maybe in our case every worksheet, but every piece of the course should be a new chapter of that story. And you need to, we need to have little kind of thread lines, storyline connecting things together. He had a couple other pieces of advice, like show up on time and be prepared. Okay, so show up on time, be prepared, and a course should tell a story. So we try to make this course tell a story. So this, you can maybe barely see this, but this is a picture of a truss. And actually, this is a real-life picture of a truss, and this is a kind of schematic diagram of a truss. And you can see things that weights, loads that it is bearing, and then you can see it's supported on these two supports. And it's an example of a problem that you'll see if you take a structures course that you can solve systematically, step by step, using Newton's three laws, especially once we have studied these ideas, the key topics of vectors and forces and torques. So we're only a chapter or two away from getting to forces. That's our first important key idea. And then when we get to chapter 10, which is quite a challenging chapter, we'll finally use vectors in 2 dimensions, whereas we've only been using vectors in 1 dimension so far, and one-dimensional vectors they might as well just be numbers with signs attached to them. But 2-dimensional vectors really need to be vectors. And then we get to chapter 12, we'll study torques. And then you'll really have the toolkit that you need to be able to analyze structures, and we'll try that out. Okay, so to analyze structures, you need a thorough understanding of forces, torques, which, by the way, engineers call moments, and vectors. So we're building up that toolkit, and then we're going to see what we can do with that toolkit in November. So Professor Wesley tells us a course should tell a story. To analyze structures, you need a thorough understanding of forces, torques, and vectors. Professor Farley tells us that. He's been teaching structures here for a couple of decades. And to understand forces well, you need a solid grasp of how forces affect motion. You need to know how different forces relate to one another, and you need to know how objects interact with one another via forces. In chapters 2 and 3, we studied the key concepts of motion: position, velocity, acceleration, etc. So it's like how to describe motion mathematically and with graphs. In chapters 4 and 5, we studied 2 key conservation laws: momentum and energy. And we saw some of the restrictions that the momentum law and the energy law place on how colliding objects can interact with one another. Finally, when we get to chapter 8, about a week from now, we will discuss forces. And we are preparing your mind for forces in chapters 6 and 7 by learning a few more of the restrictions that are imposed as a consequence of momentum and energy conservation on how objects can interact with one another. So then some of the more often misquoted or misused or misunderstood aspects of Newton's laws may be a little bit less counterintuitive to you if we've prepared your mind ahead of time. For example, this idea that for each action there's an equal and opposite reaction is often used in ways that are not actually correct statements of Newton's third law. And we will understand in the coming chapter or two that really Newton's third law is a consequence of the fact that when two objects push on, well, if one object pushes on another, then that second object pushes back. And it's just exactly analogous to the idea that a system, an isolated system of two objects, their two momenta change together. So if two objects interact with each other, if object A changes the momentum of object B this way, well, then object B must change the momentum of object A this way in such a way that the sum of the two momenta is unchanged. And that's true for every pair of interactions between two objects. So we'll see what the consequence of that is for forces. Okay, now there is a key concept in chapter 6 called inertial reference frames. And this is a chapter 6 topic that baffles most students. And you say, what is an inertial reference frame? And one reason this is so important is because Newton's first law, when we get to it, will say, in an inertial reference frame, an object at rest remains at rest, and an object moving at constant velocity continues to move at that same constant velocity unless acted upon by an unbalanced force. And you say, well, what is an inertial reference frame? And the definition of an inertial reference frame that we'll use sort of casually in our terrestrial physics course is that it is a reference frame which is not accelerating or rotating with respect to some axis embedded on the surface of Earth. Now, if you have a sort of lawyer-like mind, or if you've studied physics before, you will notice, of course, that Earth itself is accelerating and Earth itself is rotating. And the fact that Earth accelerates actually has important implications for the tides, and the fact that Earth rotates actually has important implications for the weather. So it's not strictly true, it's not really precisely true that a reference frame anchored to Earth is 100% inertial. It is for most intents and purposes inertial, but really to be a completely inertial reference frame, you have to be at rest and not rotating with respect to the fixed stars, you know, the most distant stars that you can see. But it's a very, very good approximation, except for things that are extremely large or things that are moving extremely fast, that the surface of Earth itself is an inertial reference frame. Actually, that also ceases to be true like during an earthquake when the surface of Earth itself is shaking back and forth. But anyway, for the problems that we'll solve in this course, like the sidewalk in front of the building is an inertial reference frame. So anything which is not rotating with respect to or accelerating with respect to, say, the sidewalk in front of the building is usually, for our purposes, an inertial reference frame. But sometimes you have to step back and say, well, is it really inertial? Is it really not rotating, not accelerating with respect to the distant stars? So let's go back to the simple approximation that the surface of Earth itself is, in fact, an inertial reference frame, which is an assumption we'll use everywhere in this course, except maybe if we ever don't assume that, we'll say so explicitly. So imagine yourself trying to pour a cup of coffee while standing up on an airplane which is cruising smoothly at constant velocity. It's actually no problem. You can walk back and forth. You don't have to balance yourself on the seats to walk back and forth. You could juggle. You could pour a cup of coffee. A flight attendant can pour you a cup of coffee. It's no problem. But now imagine trying to do that same thing, walk back and forth to the lavatory, or pour yourself a cup of coffee, or take your soft drink bottle and pour it into a cup while the airplane is in the middle of takeoff, or in the middle of landing, or is turning sharply, or is experiencing turbulence. So your eye and your hand are working from the perspective of a non-inertial reference frame in that second circumstance. Okay, so imagine that you are on an airplane at cruising altitude, the airplane is moving at constant velocity, smooth flight, and then imagine under those circumstances trying to pour yourself a cup of coffee, or maybe a flight attendant pouring you a cup of coffee. It works just fine. Here we are moving at constant velocity, and I seem to have no trouble at all pouring. I guess you wouldn't do this in real life, but pouring and unpouring a cup of coffee, it seems to be a piece of cake. By contrast, suppose we're moving at a non-constant velocity. Whoa! Ah!
There it is.
Oh, that was pretty good. So in that case, the inside of the airplane certainly is accelerating with respect to the fixed stars. Okay, and in that case, the usual rules of physics don't work. And if you want to use the usual rules of physics, you have to analyze the situation from the perspective of an inertial frame. And in the case of the passengers on that airplane, the way you would analyze it from the perspective of an inertial frame is you can imagine if the airplane is transparent, and then you anchor a camera on the ground and you look up at the inside of the airplane from the perspective of the camera which is sitting on the ground. And then you can clearly see that the airplane is shaking up and down or changing direction. And then the motion that you see will make sense. But if you're watching what's happening inside that airplane, which is taking off or landing or turning sharply or experiencing turbulence, from the perspective of a camera which is mounted on the ceiling of the airplane, then what you see won't make sense. You'll see things spontaneously accelerate with no apparent force acting on them. Well, we don't know the word force yet, but okay. And I'm going to show you an illustration of that with two different cameras from different perspectives in a moment. But if you want a 1960, literally 1960 video, what is that? That's 60 years ago. Here is a link to an educational video made, I think, in Canada in 1960 about frames of reference. It's kind of fun to watch. If you do want to watch it, email me 3 or 4 sentences outlining what you learned from the video, just enough, enough to convince me you actually watched it and got something out of it, and I'll give you extra credit for that. The extra credit that I assign will be basically proportional to whatever I can glean from your description of the effort that you put into watching it, kind of what you got out of it. So, an extremely terse summary will get a pretty small extra credit, and if you, kind of give me some detail that convinces me that you grasped something from it and you put some time into watching it, then that's worth more. So it's up to you how much time you want to put into it, if you do it at all. Once again, textbook chapter 6 includes only a few key ideas, but some of these key ideas, if you do look through the book, are kind of obscured by notation and equations. Okay, so the law of inertia is one big idea from chapter 6, and it's also known as Newton's first law. In an inertial reference frame, an isolated object at rest remains at rest, and an isolated object in motion keeps moving at a constant velocity. Isolated means that there's nothing outside of that object pushing or pulling on that object. And in the language of chapter 8, a couple chapters from now, we'll say there are no external forces acting on it, or if they are, they're in balance with each other. So there are no, in Newton, the way if you took physics before, you've probably heard no unbalanced force. In other words, the vector sum of forces acting on the object must be non-zero. But in the language that we've used so far in this book, an isolated object at rest remains at rest. That means there's nothing pushing or pulling on it. And an isolated object in motion keeps moving at constant velocity. So you can't feel the difference between being at rest in Earth's frame versus being at rest in some other inertial reference frame. And Professor Farley always likes to say, if you grew up, you spent your whole life on a locomotive moving at constant velocity on a smooth railroad track, or if you were in a wagon, or vehicle moving absolutely at constant velocity, it's a smooth road, not a bumpy road, you could not tell the difference until you looked out the window. You would not know. And as a matter of fact, if you're fallen asleep on a train or a car or an airplane, you know that you really can't sense that you're at motion until you either look out the window or the vehicle accelerates somehow. Maybe the road becomes bumpy, or you speed up, slow down, or change direction. Okay, so you know this. In fact, also the experience of riding in an elevator, you can feel when the elevator accelerates, but you cannot feel when the elevator is moving up and down at constant velocity. Although you can sometimes hear the whistling of air past the cabin of the elevator, the cab. So imagine you're sitting on an airplane, pouring a cup of coffee, juggling, maybe tossing a single ball into the air and catching it. Yes, I don't really know how to juggle, but I guess I could juggle one thing, right? So, okay, imagine you're doing that, and if the airplane is cruising at constant velocity, you can do it. It's no problem, right? Piece of cake. It's the same as if you were standing on the sidewalk outside of our physics building. But now what if you try to do the same thing while the airplane is screeching to a halt on the runway immediately after landing, or while you're experiencing significant turbulence, or while the airplane is making a sharp turn to adjust its course? I think from experience that suddenly that doesn't work. You have to grab onto the seat to balance yourself, or the flight attendants are not going to be pouring you a cup of coffee under those circumstances. Or if you have some workout in front of you on the little airplane tray table, sometimes it just spontaneously falls on the floor when the airplane accelerates. And I have an illustration of that. If the physics works when the cart is standing still, that the ball goes up in the air and comes back down and is caught, then the physics still works if the cart is going at constant velocity. So this is basically the same problem as, well, I'm riding on an airplane at cruising altitude, the airplane's going at constant velocity, and I throw the ball up and down. Maybe I'm bored, I'm sitting in my seat, I throw the ball up and down. But then suppose I try the same thing. I'm doing this, I'm sitting on the airplane, and we're approaching the runway for a landing, and then just after we touch down, the pilot reverses thrust and the airplane suddenly slows to a halt. Then it'll appear to me as if the ball just spontaneously shot forward. So imagine that the cart is our airplane chassis, and now here I am tossing the ball up in the air. Here I am tossing the ball up in the air and catching it while we're at cruising altitude. Piece of cake. By contrast, here I am tossing the ball up in the air and catching it when the airplane is screeching to a halt after touching the runway. So from the perspective of the person in the airplane seat, the ball went up and then shot forward. But from the perspective of the ground, it makes sense what was happening. The ball was tossed upward, but it also had a forward velocity, and then it just kept going on that arc. So the law of inertia states that in an inertial reference frame, any isolated object which is at rest remains at rest. Any isolated object in motion keeps moving at constant velocity. So now imagine you're at a jet airplane that has just landed and is in the midst of screeching to a stop on the runway. You are wearing your seatbelt. Is the frame of reference in which the airplane is at rest an inertial frame? What does that mean? So the frame of reference in which the airplane is at rest, that means that is the set of axes seen, observed by a camera which is anchored to the ceiling of the airplane, for example. If you were to mount a camera on the roof of the ceiling of the airplane, and then maybe you could even sketch out a coordinate system. You could draw a set of coordinate axes up and down the aisle and across the seats of the airplane, so that way your camera can track the position of, say, a baseball, finding its way back and forth around the passenger cabin. So that is the frame of reference. The frame of reference is like the set of axes that I use to observe the world. So if you observe the inside of the airplane from the perspective of that frame, the frame seen by the camera, which is attached to the roof, attached to the ceiling of the airplane. When you do that, if you look at the seats of the airplane, those seats are at rest according to that camera. And the airplane body, the airplane chassis is at rest as seen by that camera. The airplane itself may not be at rest, but it will not be moving with respect to that camera. And so if you imagine that you're using that camera to read off your coordinate system of what's happening, that is the frame of reference in which the airplane is at rest. It's the frame of reference observed by a camera mounted to the ceiling of the airplane. So, the frame of reference in which the airplane is at rest, is that an inertial frame? So think about that. I'll answer it for you in a minute, but think about it. And a way to help you to think about that is, will a marble initially sitting at rest on the floor of the airplane, as observed from the frame in which the airplane is at rest? In other words, as observed by a passenger with the window shades down, or better yet, as observed by the camera which is attached to the ceiling of the airplane interior, will that marble remain at rest as the airplane screeches to a stop? And I think no and no. In other words, the inside of the airplane, you draw a set of axes. You could say, whatever, x equals 0 is the back of the airplane. You can draw x equals 1, 2, 3, you can maybe each row of seats is maybe 1 meter up on your x-axis. So that's a set of coordinate axes attached to the airplane. And then you have your marble, and you say, what's the x-coordinate of that marble? And it's sitting on the floor of the airplane. Or maybe it's sitting on your little tray table in front of you because you disobeyed the orders of the flight crew and you did not fold up your little table. Then as the airplane screeches to a stop, I think you're going to see that marble shoot forward toward the front of the plane for no apparent reason. Or if it's on the floor, you're going to see that marble shoot forward toward the front of the plane for no apparent reason, because you don't see anything pushing on it. And how can that happen? Why does it make sense? It's because you're not analyzing the motion from the perspective of the ground, or something moving at constant velocity with respect to the ground. So if instead you look at that situation from a camera mounted on the ground, and the walls of the airplane are transparent, then you will see that, as a matter of fact, the marble just keeps doing what it was doing, but the airplane slows down underneath the marble. And you say, oh, that makes sense. You see, the airplane is slowing down because the airplane is applying its brakes, but the marble is able to just keep rolling freely. So the marble actually continues doing what it was doing before the airplane put on its brakes, and it's the airplane that's slowing down underneath the marble. So there's nothing inexplicable happening if you look at it from the perspective of a camera mounted on the ground. But if you look at it from the perspective of a camera mounted inside the airplane, you see something that doesn't make any sense. So I'd say D, it's not an inertial frame, and the marble will not remain at rest. It will shoot forward if the plane is, screeching to a stop. It'll be accelerating, or maybe an airplane has just landed and it's abruptly slowing down. Then I'll put my marble here, and then, whoa! So here is Einstein riding on the school bus. If the school bus is moving at constant velocity, then the ball just stands still on the floor of the school bus and everything makes sense. But if the school bus driver jams on the brakes, then what we see from Einstein's perspective is the ball, like spontaneously, just shoots forward with it. Suppose I'm a passenger on a train that is speeding toward New York City at 40 meters per second, heading north. In search of coffee, I walk toward the back of the train at 2 meters per second, just as the train whizzes past Princeton Junction. From the perspective of a passenger watching me from the train platform, my velocity is, what is my velocity? So the train is going north at 40 meters per second. And meanwhile, I'm walking backward toward the back of the train at 2 meters per second with respect to the train. So the person standing on the train platform at Princeton Junction sees me moving north at 38 meters per second. Does that make sense? So you might want to draw yourself a little picture. But the train is going north at 40 meters per second, and I'm walking backward toward the back of the train at 2 meters per second. So a person standing on the train platform sees me moving forward at 38 meters per second. That's northward. The velocity of me with respect to Earth equals the velocity of the train with respect to Earth plus the velocity of me with respect to the train. Let's say that again. The velocity of me with respect to the Earth equals the velocity of the train with respect to the Earth plus the velocity of me with respect to the train. Whoa. My velocity with respect to Earth equals the train's velocity with respect to Earth plus my velocity with respect to the train. You might have to pause and scratch your head a little bit and think about that last statement. I'm driving east at 50 kilometers per hour. A little kid looks out the window of a westbound car that is going 40 miles per hour. From the kid's point of view, what is my velocity? Oh, uh-oh. So I'm going east at 50 kilometers per hour, and a little kid is in a car that's going west at 40 kilometers per hour. I think the little kid sees me going east at 90 kilometers per hour. East. Yeah, I think it's D, delta. I think the little kid sees me going east at 90 kilometers per hour. And again, the way you look at that is you say, I guess you can say the x velocity of me with respect to the kid is the x velocity of me with respect to Earth minus the x component velocity of the kid with respect to Earth. So I take my x component of velocity, let's say the x-axis points east. Let's have east is the x-axis. So I think you can say I'm going east at 50 kilometers per hour. So me with respect to Earth is 50 kilometers per hour east, which we'll say is the plus x direction. The kid is going west at 40 kilometers per hour with respect to Earth. So I take this minus this, and I get 90. So 40 kilometers per hour west is negative. That's in negative x direction, right? So west is in the negative x direction. So I have 50 minus negative 40 is plus 90. So I say, from the kid's point of view, my velocity with respect to the kid is 90 kilometers per hour to the east. So that's D, delta. That's pretty tricky. You might want to pause and make sure you understand that too. I'm driving east at 50 kilometers per hour. A truck driving east at 60 kilometers per hour overtakes me. As I look out my window, how fast does the truck appear to be moving? Well, I think the truck appears to be moving 10 kilometers per hour to the east. So again, this is V sub x of truck with respect to me is V sub x of the truck with respect to Earth minus V sub x of me with respect to Earth. Yeah, truck with respect to me is truck with respect to Earth minus me with respect to Earth. So this is plus 60 kph, that's in the east direction, and then you have minus 50 kph, and it's also in the x direction. I'm going to let the x-axis point in the east direction here. So the answer is plus 10 kilometers per hour. I didn't ask for a direction, but the direction is, plus 10 kilometers per hour, and the direction is to the east. So from the perspective of me looking out my window, the truck seems to be moving east. It seems to be moving east at 10 kilometers per hour. So the only key quantitative idea in chapter 6, so there are some key conceptual ideas, is center of mass. Center of mass is basically a weighted average of positions. So, right, so in vector notation, nobody likes the vector notation. The position of the center of mass is mass 1 times the position of object 1 plus mass 2 times the position of object 2, and so on upstairs in the numerator. And in the denominator, it's just the sum of all the masses. Maybe more naturally, the x-coordinate of the center of mass is the mass of object 1 times the x-coordinate of object 1 plus the mass of object 2 times the x-coordinate of object 2, and so on for however many objects constitute the system you're talking about. And then in the denominator, you have the sum of all of those masses. So it really is just the same as the familiar formula of a weighted average. So the masses are the weights, and the thing you're averaging is the position, or the x-coordinate. By the way, if an object has an axis of symmetry, then its center of mass lies along that axis of symmetry. So if you had a, well, this isn't a perfect rectangle, but if you had a nice rectangular object, and its center of mass would lie along this symmetry axis, and it would lie along this symmetry axis. That's assuming it's of uniform density. So if you have an object of uniform density that has a symmetry axis, then the center of mass will lie along any symmetry axis you can identify. That's often a very useful trick for finding center of masses. And then it turns out in physics that if you want to analyze the motion of a complicated object, an object composed of many pieces, I don't like this dry erase marker is an example, or this remote control is an example. You want to analyze the motion of a complicated object. It's often useful to consider separately the motion of the center of mass and the motion of the various internal parts with respect to the center of mass. And we'll see once we get to the language of chapter 8, the reason why that is useful is to analyze the motion of the center of mass, you only have to consider the forces that are outside of that system, outside of that object. So you don't have to consider the internal forces where the little pieces of the object are pushing on each other. So you're considering things that are outside the object and how they push or pull on the object. You're not considering how the little constituents of the object itself push on each other to analyze the motion of the center of mass. And I have an illustration of this, tossing a complicated object in the air. And you'll see that even though the constituent parts of the object may travel in some complicated motion, the center of mass of the object follows the same familiar arc that, say, a baseball would follow. So here's an ordinary ball, so we're kind of accustomed to seeing it move in a fairly simple way. And we can look at some more complicated objects. And if we look at, I don't know, here's a twirling hammer. Now, you'll see that there's a kind of a spinning motion of the hammer about its center of mass, but its center of mass, which stands out because it's brightly colored, you'll see traces out the same simple motion that the tennis ball did a moment ago. Okay. Good, all right. And then we could take another complicated object. Here are 3 tennis balls tied together. Or we could take another complicated object. Here's a rubber chicken. And I think in every case, even though the motion of the constituent parts of this complicated object might have been somewhat complicated, the motion of the center of mass was still fairly simple and followed that same consistent pattern. So this is one usefulness of this idea of center of mass. Okay, let's say we have an x-axis. So this is our x-axis. The x-axis points to the right, and it's labeled in meters. So here's -4, -3, -2, -1, 0, +1, +2, +3, +4. And let's say we have a 1 kilogram object here at x equals -3 meters. And we have a 2 kilogram object here at x equals +2 meters. So I just copied, there's nothing up there. So I just copied it down here. So we have 1 kilogram at, so we have 1 kilogram, m1 equals 1 kilogram at x1 equals minus 3 meters. And we have m2 equals 2 kilograms at x2 equals plus 2 meters. Okay, then what is x center of mass? So I would say x center of mass is m1 x1 plus m2 x2 over m1 plus m2. And that is 1 kilogram times minus 3 meters plus 2 kilograms times plus 2 meters. And in the sum of the two masses, 1 kilogram plus 2 kilograms. Well, here, I'll just write it out. 1 kilogram plus 2 kilograms, which is 3 kilograms, right? So what does that work out to be? Okay, so that's 1 kilogram times minus 3 meters plus 2 kilograms times plus 2 meters divided by 3 kilograms. So downstairs we have 3 kilograms. Upstairs we have minus 3 and plus 4. So minus 3 plus 4 is plus 1. So that's plus 1 kilogram meter. And the answer is 1/3, well really plus 1/3 meter. And I think that makes sense because it tells you the center of mass is around here. And it makes sense that it's closer to the 2 kilogram mass than it is to the 1 kilogram mass. In fact, I think it should be twice as far away from the 1 kilogram mass as it is to the 2 kilogram mass. So it seems like it's 1 2/3 units away from this guy. And it's 1, 2, 3 1/3. Let's see, so there's 3, 6, 9, it's 10/3 away. It's 10/3 away from this one, and it's 1 5/3 away from this one. So I think that makes sense. Yeah, so it's 1 2/3 away from this one, and it's 1, 2, 3 1/3 away from that one. So I think that makes sense. It should be 2 times as far away from the 1 unit of mass as it is from the 2 units of mass. Okay, so that was an example. Here's our next example. What is the x-coordinate of the center of mass of this pair of masses, a system of 2 masses? So we have m1 equals 3 kilograms at x1 equals minus 1 meter. And we have m2 equals 1 kilogram at x2 equals plus 3 meter. And so we can say x center of mass is m1 x1 plus m2 x2 over m1 plus m2. And that is 3 kilograms times minus 1 meter plus 1 kilogram times plus 3 meters divided by the sum of the two masses, which is 4 kilograms. And that equals, so 3, that's minus 3, and plus 3, it's 0. Okay, so it is 0 meters. And let's see if that makes sense. It seems like the center of mass is here at 0 meters. Actually, that does make sense because this is 1 unit of mass, that's 3 units of mass. So we expect this to be 1, 2, 3 units away, and this is 1 unit away. We expect the 1 unit of mass to be 3 times as far away from the center of mass as the 3 units of mass, just for 2 things. So that makes sense. The center of mass here is at 0 meters. Okay, the other quantitative idea from chapter 6 is center of mass velocity. It's the velocity of the center of mass of a system of objects. So as I wrote up here, well, you could write it in vector form. So the velocity of the center of mass is just the mass-weighted average of all of the velocity vectors. It's probably going to be more intuitive if you say what is the x component of the center of mass velocity. So you have the x component of velocity for object 1 times mass 1, and you have the x component of velocity of object 2 times mass 2, and so on. And the sum of the masses downstairs, so I wrote it up here too. You have mass 1 times v1x plus mass 2 times v2x, and so on, the sum of all the masses. So it's basically the mass-weighted average of all of the x components of velocity of the objects in whatever system you are considering. You could notice, if you like calculus, you could notice that the second quantity is the derivative with respect to time of this first quantity, since the masses are all constants, but the x-coordinates are all variables. So it turns out an isolated system's center of mass velocity cannot change. This is hugely important, it turns out. So if you have a system of objects, they might be pushing on each other, but as long as there's nothing outside of that system pushing or pulling on anything inside of that system, the velocity of that system's center of mass will be constant. And I think you saw that, well, you know that the momentum of an isolated system is constant. And you might notice that the momentum of the center of mass of a system is just the total mass of the system. So you might, so if you like math, you might have noticed that the momentum of the system, is the total mass times the center of mass velocity of the system. The x-coordinates are probably easier to envision. So you already know that the momentum of a system of isolated objects is constant. And so as long as the mass of that system is constant, which will be true unless the system is somehow jettisoning some of its mass. I mean, a rocket will do that. A rocket will throw some of its mass away, but that's kind of an unusual case. So if you have an isolated system of objects, then the center of mass velocity of that system is constant. That's just a consequence of the momentum of that system being constant. Yeah, so you can see this by noticing that the numerator in the center of mass velocity is the system's total momentum, which you know is constant for an isolated system. Yeah, so this upstairs here, this numerator, is what you're accustomed to looking at as the, right, so this is P sub x of the system, and then this is divided by the total mass. So you know that the total momentum in the x direction, let's say, of an isolated system is constant. So as long as the total mass of that system is not changing, like it's not throwing away some of its mass by jettisoning it, like kicking it out of the system, then you know the center of mass velocity of that system is constant. So if you observe this system from a camera that is moving at VCM, at the velocity of the center of mass, then the system's center of mass will appear to be at rest. Okay? So if you take a system of objects and you figure out how fast is its center of mass moving, and now I take a camera and I make that camera move at the same velocity as the center of mass of the system, and I use that camera, which is moving with the center of mass of the system, and I use it to observe the system, from the perspective of that camera, the system will appear to have its center of mass at rest. In other words, the center of mass of the system will appear to have zero momentum. That's why the textbook calls the center of mass frame of reference the zero momentum frame, the ZM frame, because the system's momentum is zero as seen from that frame. In other words, as seen by a camera which is moving at the same velocity as the center of mass velocity of the system. Students, year after year, hate this. They find it baffling. If you find it baffling, don't worry about it. You're in good company. It's convenient that ZM and CM sound the same. So if you see the textbook say ZM frame, you can think that it says CM frame and you're just fine. Actually, more people in the physics world say CM frame rather than ZM frame. Our textbook is being innovative by saying ZM frame. So just remember that the center of mass velocity of a system is the velocity of the center of mass. It's the mass-weighted combination of the velocities of the constituents of that system. My friend and I take our little track and our two little colliding carts, and we set them up, probably in the dining car, on board a moving train. And it's a train which is moving north at a constant velocity of 30 meters per second. And with our little track aligned with the train axis. Okay, so we have our little colliding carts track, and we're doing this in a dining car on an intercity train, and the axis of the little collision is going to be parallel to the axis. The axis of our little cart is going to, of our little track that we're colliding the carts on, will be parallel to the axis of the train. So I push a 1 kilogram cart north toward my friend at 1 meter per second. She pushes a 1 kilogram cart south toward me at 1 meter per second. As seen by a camera mounted on the ceiling of the train, what is the velocity north of the center of mass of the two-cart system? Well, I would say this is VCMX, as seen by the camera on the ceiling of the train. So this is 1 kilogram times 1 meter per second plus 1 kilogram times minus 1 meter per second, and then divided by 1 kilogram plus 1 kilogram. Okay, so that's going to be 0 because you have 1 times 1 plus 1 times minus 1, so that's 0. So this is 0 meters per second. So I think I like answer E here, 0 meters per second. As seen by a camera mounted on the train platform at Princeton Junction, which is looking in the window as we go by, what is the northward velocity of the center of mass of the two-cart system? Well, I think in that second case, the answer is going to be plus 30 meters per second, right? So it's going to be, it'll be plus 30 meters per second. You say, how did I get that so fast? Well, I guess I could say this is as seen from the train platform, like at Princeton Junction. It's like the sidewalk, basically. I have VCM, the X component. So our 1 kilogram cart is moving. So I push north toward my friend, and the train's moving north. Yeah. So this is 31 meters per second. And then we have the other 1 kilogram cart, which is moving toward me. And so this is 29 meters per second. And then we're going to divide by the same 1 kilogram plus 1 kilogram. So the answer is 30 meters per second. Yeah, because 31 plus 29 divided by 2, it's just the average of 31 and 29. That's 30. You could also say, well, you see, I take the center of mass velocity as seen in the train. See, it turns out VCMX of the system, that's the system of two carts, with respect to Earth. Earth is like the person standing at Princeton Junction, equals VCMX of the system with respect to the train plus VCMX of the train with respect to Earth. So the system with respect to Earth, this is this plus 30 meters per second. And the system with respect to the train was 0 meters per second, and then the train with respect to Earth was plus 30 meters per second. So that's how I got the initial value so quickly. I just added 30 because I said, well, it's not moving with respect to the train, and the train's moving 30 meters per second north with respect to the platform, which is at rest on Earth. And so that system must be moving 30 meters per second north with respect to Earth, with respect to that platform, which is anchored at Princeton Junction. Is one of these two cameras watching from the 0 momentum frame of the two-cart system? Well, yes. As a matter of fact, the camera mounted on the ceiling of the train happens to be watching from the perspective of the 0 momentum frame of this system, because the momentum of this system as a whole, as seen by that camera on the ceiling of the train, is 0, right? So it turns out that that is the 0 momentum frame of this particular system, because this particular system's momentum happens to be 0 in the frame of the train. Now, if I had pushed my cart at 2 meters per second and my friend had still pushed her cart at 1 meter per second, then that would no longer be true, because this system of two carts would have a momentum which is non-zero with respect to the ceiling of the train. But with the numbers as stated, the perspective observed by the camera mounted on the ceiling of the dining car to the train is the 0 momentum frame of that system. It's pretty tricky conceptually, but working with the numbers isn't that bad. It's just kind of a tricky concept. Okay, similar example with different numbers. A friend and I take our little track and our two little colliding carts, and we set them up, probably in a dining car, on board a moving train. The train is moving north at a constant velocity, 30 meters per second. And our little track is aligned with the train axis. I push a 1 kilogram cart north toward my friend at 3 meters per second. She pushes a 2 kilogram cart south toward me at 6 meters per second. As seen by a camera mounted on the ceiling of the train, what is the velocity of the center of mass of the two-cart system, letting the x-axis point north? Well, I would say v x cm is, okay, so m1 is 1 kilogram, and vx1 is plus 3 meters per second. Right, I push it north, so north is plus 3 meters per second. And then she pushes a 2 kilogram cart, and then south is minus x, so that's minus 6 meters per second. And then the sum of the two masses is 3 kilograms. 1 kilogram plus 2 kilograms is going to be 3 kilograms. So this will be plus 3 minus 12, so that's minus 9. So that's minus 9 divided by 3. Right, so here's minus 12 plus 3. So that's plus 3 kilogram meters per second. Oh, wow, that's units of momentum, you see? Minus 12 kilogram meters per second divided by 3 kilograms. So if minus 12 is minus 9 divided by 3. So there's minus 3 meters per second. Okay, so I say the answer is minus 3 meters per second. In other words, 3 meters per second to the south, as seen by that camera on the ceiling of the train. Now, as seen by a camera mounted on the train platform Princeton Junction, which is looking in the window as we go by, what is the northward velocity of the center of mass of a two-cart system? Well, the quick answer will be, so then, as seen from Earth, the Earth frame, I could say from Earth, that's going to be VXCM. I'm just going to add 30. So that's going to be plus 27 meters per second. And that's because I'm going to say VXCM of the system with respect to Earth is VXCM of the system with respect to the train plus VXCM of the train with respect to Earth. Okay? So the velocity of the system with respect to Earth is the velocity of the system with respect to the train plus the velocity of the train with respect to Earth. And this value turned out to be plus 27 meters per second. And this was this number we worked out, minus 3 meters per second. And then this is plus 30 meters per second. So that's how I got that. But let's work it out a different way. Let's work it out as seen, as measured by the person on the train platform. So what the person on the train platform sees is VXCM is 1 kilogram. So this cart, see, it's plus 3 with respect to the train. So this person sees this cart moving at 33 meters per second. And then there's 2 kilograms. And this person sees it moving at 30 minus 6 is 24 meters per second. And then the same thing downstairs, 3 kilograms downstairs. And so that's 33 plus 48 divided by 3. Oh, so that's like 11 plus 16. So that's 27. Yeah, 27 meters per second. Same answer, 2 different ways. One is using the camera on the train platform on Earth to measure the 2 velocities separately. And the other is saying, well, let's just take the system velocity as measured on the train and then add to that the velocity of the train with respect to Earth. So, either way, we say, as seen by a camera mounted on the train platform at Princeton Junction, it's 27 meters per second is that center of mass velocity of the system along the x-axis, which is the axis pointing north. Is one of these 2 cameras watching from the zero momentum frame of the 2-cart system? No, because it would only be the zero momentum frame if it turned out that that system's momentum were 0 as seen in that frame. In that frame, in other words, by that camera. There is no camera, neither of these 2 cameras sees that system having 0 momentum. Therefore, neither of those cameras sees that system having a 0 center of mass velocity. So no, neither one is watching from the zero momentum frame of the 2-cart system. So the answer here is no. On the previous page, it was yes for the camera on the ceiling of the train, but no for the camera at the train station. In this case, it's no in both cases. If I observe a system from its zero momentum reference frame, what can I say about its center of mass velocity? This is, it's kind of like a really, it just depends on understanding the textbook's concept of zero momentum frame. So if you didn't look at all the textbook chapter, this may not even be worth considering. But the center of mass velocity, as seen from the zero momentum frame, is 0. Okay, so this is the correct answer. And when observing from Earth's frame of reference, a system center of mass velocity will be the same as the velocity of the zero momentum reference frame. When observing from Earth's frame of reference, the system center of mass velocity is the same as the velocity with respect to... Well, this is also a true statement. So I guess B and C are both true. So I guess I actually like F, because B and C are both true. Center of mass velocity, as seen from the zero momentum frame, is the same as velocity. That's not true. No. A is definitely not true. Okay, A is definitely not true. B and C are both true, so I like F. But this isn't really a hugely important point. But what is the zero momentum frame? The zero momentum frame is like the perspective that you would see if you looked through a camera, and that camera is somehow fixed to the center of mass of the system. So if you have this system of several objects, and you arrange for a camera to be moving at the exact same velocity as the center of mass of that system, so then that camera looks at the system with whose center of mass it is co-moving, then by that definition, that camera sees that the center of mass of that system is not moving. That's because you say, okay, I'm going to observe the center of mass velocity of a system. I'm going to set up a camera which is moving with the center of mass of that system. And now that camera looks down at the system, and what does it see? It sees that the system is not moving. Because from the perspective of a camera which is moving with the center of mass of the system, the velocity of the center mass of that system is zero. The parts might be moving away from each other or toward each other, but the center mass of the system, as seen by that camera, is zero, and that camera is defined to be moving at the velocity of the center of mass of the system. So that's called the zero momentum frame. That's because if you arrange somehow for a camera to move along with the same velocity as the center mass of a system, if that camera looks at the system and measures the system's momentum, the answer will always be zero. Because a camera whose velocity is the same as the velocity of the center mass of the system, when it looks down at the system, will see that the momentum of that system is zero. That seems like a lot of words to say something that once you get it, you say, why did you use so many words for that? A few more key ideas from Chapter 6, if you happen to skim through Chapter 6. An isolated system's center of mass velocity cannot change. And again, that's true because an isolated system's momentum cannot change. And the center of mass velocity of a system is proportional to the momentum of the system. A somewhat obscure consequence of this fact is that even in a totally inelastic collision, it is not necessarily possible to convert 100% of the initial kinetic energy into other forms, like heating up or mangling, etc., the colliding objects. Actually, somebody asked me this. It's actually pretty interesting. So if you start out with a system whose center of mass is moving, then even if you have a totally inelastic collision, so the parts then afterward are not moving with respect to each other, then there's still some kinetic energy left at the end because momentum of the system as a whole stays constant. So that's kind of an interesting fact. So momentum conservation will require that the center mass velocity cannot change. So if the center mass is moving initially, it has to keep moving after the collision. So in the textbook, there is this concept of the convertible portion versus the translational portion of a system's kinetic energy. That idea is worth remembering, but the math is not worth remembering. If we arrange an elastic collision between these two objects, then the kinetic energy at the end of the collision is the same as the kinetic energy at the beginning. And if we arrange a totally inelastic collision, in this case, the kinetic energy at the end is zero. By making the move in opposite directions at the same speed, then the initial momentum of the system is zero, and the final momentum of the system is zero. Meanwhile, the initial kinetic energy of the system is non-zero. The final kinetic energy of the system is zero. But what if I do this in a different way? What if I collide these two objects, and again, to make it simple, I've made them equal masses. What if I collide these two objects in such a way that the initial momentum of the system as a whole is non-zero? That the velocity of the center of mass of the system is non-zero. Even if I collide them in a way that is totally inelastic, there's still some kinetic energy in the final state because I can't make the initial momentum disappear. So the final momentum of the system as a whole equals the initial momentum of the system as a whole. And for that reason, the system as a whole, the center of mass of the system will still be moving after the collision if the center of mass of the system was moving before the collision. So even though this collision is a totally inelastic collision, I can't make all of the kinetic energy transform into other forms. So there are really only two equations you need to know from chapter 6. Definition of the center of mass, which is just the mass-weighted average of all the positions, and the definition of the center of mass velocity, which is just the mass-weighted average of all of the individual objects' velocities. So there is this third kind of obscure thing called the convertible kinetic energy. So again, you can cover your ears and stop listening if you like, but the kinetic energy has two parts. There's the convertible part, and then there's the, I think this is called the translational part. And the translational part is 1/2 times the total mass of the system times the center of mass velocity of the system squared. And then the convertible kinetic energy is just the kinetic energy minus this translational part. Or you could say the convertible kinetic energy is the kinetic energy minus 1/2 m total VCm squared. And what does that mean? It means even if all of the objects in the system collide and stick together, so that none of the objects after the collision are moving with respect to one another, if the center of mass of the system was moving before the collision, then the center of mass of the system will still be moving at that same velocity after the collision. Therefore, there will still be some kinetic energy associated with the fact that the center of mass is moving. And that's what this translational part is. It's the total mass, it's 1/2 of the total mass times the square of the speed at which the center of mass of the system is moving. And so even if you make all the parts of a system stick together in a collision, only this convertible part of the initial state kinetic energy can be converted into other forms like heat, or like rearranging the shape of your bumpers or fenders in your car. So you cannot get rid, well, if the initial state has a 0 center of mass velocity, in other words, if the momentum of the system as a whole is 0, then you can, in a collision, get rid of all of the kinetic energy. So the kinetic energy afterward would be 0. But that's only possible if the momentum of the system is 0. In other words, the center of mass velocity of the system is 0. If it's non-zero, then there's always then the fact that momentum has to be conserved in the collision means that the center of mass velocity of the system will be the same before and after the collision, which means that this translational part of the kinetic energy cannot be eliminated by colliding objects with each other, even if they stick together. So the only part that you can convert to other forms like heat is the convertible part. So it's kind of an interesting idea, but you will never actually have to use this fact. If you like this idea of a center of mass velocity, or sometimes it's known as a zero momentum frame velocity, and I'd say maybe like 5% of students are willing to put up with this idea, 95% don't want anything to do with it. It turns out to be a convenient way to solve collision problems sometimes, although again, many people find it confusing enough that it's not worth doing. But if you don't mind, if you can get past the confusion, then it is an interesting simplification. So if you move into the zero momentum frame, that basically means you figure out what is the velocity of the center of mass of the system. Usually it's just two objects, okay? So you figure out the center of mass velocity of that two object system. and then you subtract it from each object's velocity. So I'm going to say that v1 initial star is just v1 initial minus the velocity of the center mass frame. And then v2 initial star is just v2 initial minus the velocity of the center mass. If you do that, then if the collision is elastic, so if the center mass of the system is not moving, then in an elastic collision, each object's velocity simply reverses sign. That's all. So v1 final star is just the negative of v1 initial star. And v2 final star is just the negative of v2 initial star. So in the center of mass frame, which our book calls the ZM frame, elastic collisions look extremely simple. The velocities just negate themselves. So each velocity after the colliding is just the negative of that velocity before colliding. That's all. So the trick is you take the velocities, you shift them into the ZM frame, and then you just negate the sign of each velocity, and then you shift back to the Earth frame. And so that sometimes turns out to be a simple way to work out problems, because it's an extra step before and after, but it makes the math completely simple. If the collision is inelastic rather than elastic, it's almost the same. It's just that v1 final star is minus e times v1 initial star, where e is the restitution coefficient. And v2 final star is just minus e times v2 initial star. And again, by star, I mean in the ZM frame. In other words, as observed in the ZM frame. How do you get into the ZM frame? You take the velocity and you subtract the center mass velocity from it. So that means that the starred velocities in my notation are the velocities with respect to the center of mass. Step 1. Shift velocities into the ZM frame by subtracting the center of mass velocity. Step 2. Write down the answer in the ZM frame, which is very simple. If it's elastic, you just have a minus sign. If it's inelastic, you multiply by minus the restitution coefficient. Step 3. Shift the velocities back into the Earth frame by adding this same ZM velocity that you subtracted in step 1. So I guess there might be some extra credit problems you can try it on, otherwise you can skip it. Although it does turn out to be kind of a useful concept that if a collision is elastic, and if you look at it from the zero momentum frame, then the result is simply that the velocities flip sign. That's actually, and it turns out to have some kind of intuitive and also some quick calculation back of the envelope value. But if you don't, most people don't like it, so you can just pretend you didn't hear it. Okay, so again, there actually are 3 pretty cool situations you can analyze easily using this zero momentum frame trick. The first such problem is when a stationary golf ball is hit by a much more massive golf club. The golf ball's outgoing speed is 2 times the incoming speed of the end of the golf club. Okay, so this is like, here's the golf club, and it has some gigantic mass. And it's moving at some speed, we'll call this m1. Okay, this is like v1x initial. And then here's the golf ball, and it's some tiny mass, m2. Okay, and it's initially not moving. So it turns out that if m1 is much bigger than m2, then v2xf is approximately equal to, and it's equal in this limit where this ratio goes to infinity, it's approximately equal to 2 times v1xi. So it's actually kind of fun to analyze that from the zero momentum frame. The second statement is it's easier to hit a home run off of a fastball than off of a slow pitch. And it turns out the result that you can prove is that, let me see. So you have, here is let's say 2 is the baseball, and it has a small mass m2, and this is Vx initial 2. Actually, I guess we should say V2x initial. V2x initial. And then we have 1 equals the bat. And so we'll call this M1. I'll make it a big M just because it's supposed to be very massive. And then this is how hard you're swinging the bat. So you tend to swing the bat pretty fast. So then here's V1x initial. And if M1 is much bigger than M2, then it turns out that V2x final is 2 times V1x initial minus V2x initial minus V2x initial. So in other words, the speed at which the ball flies off the bat after being hit is 2 times the speed of the swing of the end of the bat plus the speed of the pitch. Okay, because so the ball, yeah. So you have like you take the ball's incoming velocity and you reverse it, and then you add to it 2 times the velocity of the end of the bat. So you get essentially the speed of the ball going out toward the outfield is twice the speed of the swing plus the speed of the pitch. So it turns out it's easier to hit a home run off of a fastball than it is off of a slow pitch, because the speed of the pitch gets added into the speed of the ball coming off of the bat. See, with this minus sign just says change direction. So the ball's initially going from the pitcher toward the batter. So the minus sign means it's going from the batter back toward the pitcher and toward the outfield. So that's number 2. You can prove that also using the zero momentum frame trick. And then the third trick, actually this is really fun to see, and I have a little video clip of it, which is if you take a basketball and you put a tennis ball on top of it, and then you drop them from some initial height. So let's say that this initial height is h. Then it will turn out, and I think you need a result from chapter 7 to understand all of the why behind this, but it will turn out that this tennis ball reaches a final height, which is, so this is, let's call this h initial of the tennis ball. It will reach a final height, which is, in this limiting case where the basketball is much, much more massive than the tennis ball, and also where the collision is perfectly elastic, this is 9 times h initial. Okay, so it's actually really fun to see just how far the tennis ball flies off the top of the basketball if you drop them just touching each other. And the way you end up modeling this is you say first the basketball bounces elastically off the ground, and then the tennis ball bounces elastically off the basketball. And you can actually see from this result, you see 2v plus v pitch. So you see if the basketball collides elastically with the ground, then its velocity just reverses. And now you have the baseball problem. So you have this speed, 2 times this speed plus this speed is what this guy gets going back up. So then that ends up being 3 times the speed at which these things hit the floor. And we'll see in the next chapter that the gravitational potential energy is mgh. And we know kinetic energy is 1/2 mv squared. So if you triple the speed, then that's 9 times the energy. And 9 times the energy gives you 9 times the height in gravitational potential energy. That's where the 9 comes from. You triple the speed, and then since it's squared and v squared, you end up multiplying the energy by 9. So that gives you 9 times as much height. Okay, but that's just waving my hands. There's actually a way you can prove these things using the zero minimum frame trick. And if you really hate the zero minimum frame trick, you can step back and prove them more tediously if you want to. So I was planning to skip these as things that are obscure and leave them as topics that you could solve yourself in extra credit problems. If I hear people express some overwhelming demand, then I could work them out in some future video, but only if there's overwhelming demand. Otherwise, I'm going to leave it for, unless I hear overwhelming demand, I'm going to leave this for extra credit problems. And I think if you do choose to work them out for extra credit, I think you'll find it really kind of fun. In that idealized scenario, the final height of the tennis ball would be 9 times the initial height of the tennis ball. Let's see how well we do. Whoa! Hey, that was pretty amazing. So this is most impressive in a classroom if I drop everything from a pretty good height and you see the ball bounce off the ceiling. But if you want to try to quantify things, I'll bounce it from a relatively small height, and then you can sort of see what happens with the striped ruler here. So let me drop it from a relatively low height, and let's see what happens. We're approximating the collisions as elastic, and we're approximating the mass of the basketball as much, much larger than the mass of the tennis ball. But to the degree that those are true, then we should get this factor of 9 in height. I'm also ignoring, I think, the physical size of the basketball and the tennis ball. And then, just to make it more impressive, although very hard to quantify, I'll try it from way back in the room at a pretty good height, and maybe you'll hear the crash. Yeah, you can hear it thud against the ceiling. That is all I have to say about chapter 6. This should be shorter than your average one of these videos. And then the next chapter will be 7, which should also be pretty short, and then 8 will take us some time to get through.